Acid-base equilibrium, the pH scale, and calculations with pH, pOH, hydronium, and hydroxide. In this tutorial, we will be going over the autoionization of water, the ion product of water, the pH scale and calculating pH, calculating the concentrations of hydronium and hydroxide, calculating pOH, and finally, the relationship between pH and pOH. The autoionization of water. Consider the equilibrium expression of water, where we have two water molecules in equilibrium with the production of hydronium ions and hydroxide ions. In this system, equilibrium favors the reactants. That is, the undissociated, non-ionized molecular form of water is favored over the dissociated, ionized, non-molecular form. In other words, the formation of the hydronium and the hydroxide ions. Let's look at this more closely. Autoionization, when one water molecule donates a proton to another water molecule. Let's look at an example. The first thing that we need is the structural formulas of two water molecules. Here we have two water molecules. I'm going to call this first water molecule my acid, and I'm going to designate this other water molecule as my base. Now you might be saying, why are you calling this one the acid and this one the base? That's because this water molecule right here is going to donate one of its hydrogens, let's say this hydrogen right here, to this other water molecule. And this water molecule is going to accept that hydrogen ion. As a result, we're going to form a hydroxide ion and a hydronium ion. So I'm going to put my equilibrium symbol and draw a hydroxide ion and a hydronium ion over on the product side. So here's my hydronium ion that is formed and my hydroxide ion. The hydrogen from the acid is donated over to the water molecule acting as a base. This forms a coordinate covalent bond right here, where this hydrogen ion is sharing with the lone pair from the water molecule. So that is a coordinate covalent bond, otherwise known as a dative bond. As a result, the two electrons that were shared between this hydrogen and this oxygen are now represented here. So this hydroxide ion now has an overall charge of -1 because that hydrogen ion, which is just a proton, was donated to this water molecule. As a result of this, we form conjugate acid-base pairs. So this hydronium ion right here is the conjugate acid of this base. So these two right here are conjugate acid-base pairs, while the hydroxide ion is the conjugate base of the acid. So these two are conjugate acid-base pairs. So we can see through these structural formulas how donating a hydrogen to a water molecule and that water molecule accepting that hydrogen represents the autoionization of water. The ion product of water. Consider the equation above. The equilibrium constant expression for the autoionization of water is Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, which equals 1 × 10⁻14. Another way to express this is hydrogen ion concentration times hydroxide is also equal to 1 × 10⁻14 because we know the use of the hydrogen ion and the hydronium ion is interchangeable. In these situations, Kc is represented as Kw, which is referred to as the ion product constant for water. The value of Kw is temperature dependent. That's very important. So the pH of pure neutral water will deviate from a pH of 7 at temperatures other than 25 degrees Celsius. We'll get into that more in a later video. H2O is not included in this expression, as equilibrium expressions do not include the concentrations of pure solids or pure liquids. If a solution is neutral, Kw is going to equal the concentration of the hydronium ion, which is 1 × 10⁻⁷, times the concentration of the hydroxide ion, which is also 1 × 10⁻⁷, which will equal 1 times 10 to the negative 14. If a solution is acidic, the hydronium ion concentration will be greater than the hydroxide ion concentration. If a solution is basic, the hydronium ion concentration will be less than the hydroxide ion concentration. In all cases, it is important to remember that as the concentration of one ion, whether it's the hydronium ion or the hydroxide ion, increases, the other ion must decrease so that the product of their concentrations always equals 1 times 10 to the negative 14. The pH scale, where the hydrogen ion concentration is expressed in terms of pH. The pH equals the negative logarithm in base 10 of the hydronium ion concentration. The P in front directs us to take the negative log of the measurement that follows. So pH is equal to the negative log of the hydronium ion concentration, which may be expressed also as pH is equal to the negative log of the hydrogen ion concentration. The pH of a solution can be related to its hydrogen ion concentration by the relationship hydronium ion concentration is equal to 1 times 10 to the negative pH. And this is a general estimation for this type of calculation. Thus, a solution with a hydrogen ion concentration equal to 1 times 10 to the negative x has a pH of x, where x is a whole number from 0 to 14. The hydronium ion concentration of 1 times 10 to the negative 4 will have a pH of 4. 1 times 10 to the negative 11 will have a pH of 11. Let's look at some examples. Given the following ion concentrations, indicate whether the solutions are neutral, acidic, or basic. So the first one has a hydronium ion concentration of 4 times 10 to the negative 9. The first thing that we have to realize here is that this is a very small number. So this 4 right here is basically tiny. So we're going to disregard that 4 for right now because all we're doing is determining whether this solution is neutral, acidic, or basic. So if we take the absolute value of this negative number, since we are in terms of hydronium ion concentration, the solution is going to have a pH of 9 and will be considered basic. So again, we're taking the absolute value of this negative 9 and that's transferring over to our pH. Let's look at the next one. Hydronium ion concentration, 1 times 10 to the negative 7. So the pH is going to be equal 7, and this is a neutral solution. Finally, hydronium ion concentration is 7 times 10 to the negative 1. So the pH is going to be 1, and this is considered an acidic solution. Calculating the concentrations of hydronium and hydroxide ions. Please make sure that you have your AP Chemistry reference tables available while we're doing this, since many of these formulas can be found on that reference table. Calculate the concentration of hydronium ions in a solution where the hydroxide ion concentration is 0.01 molar. The first thing that we're going to do is write the formula Kw is equal to hydrogen ion concentration times hydroxide ion concentration. Then what I'm going to do is I'm going to rearrange this formula to solve for the concentration of hydronium ions. So again, hydronium ions and hydroxide ions can be used interchangeably. So I'm going to write the concentration of hydronium ions is equal to the Kw divided by the hydroxide ion concentration. Then I'm going to plug my values in. Kw is equal to 1 times 10 to the negative 14. The concentration of hydroxide is given to us as 0.01 molar. When I divide these two values, I get 1 times 10 to the negative 12 molar. If I take the absolute value of this exponent, my pH is going to equal 12. Therefore, this is a basic solution. Let's do another example. Calculate the concentration of hydronium ions in a solution where the hydroxide ion concentration is 1.8 times 10 to the negative 9 molar. So again, we're going to write the equilibrium constant expression for water. I'm going to rearrange this to solve for my hydronium ion concentration. Next is to plug the values in that are given, including the ion product constant for water. When I do the calculations here, my answer is 5.6 times 10 to the negative 6 molar. So that is my hydronium ion concentration. Calculate the concentration of hydroxide ions in a solution where the hydronium ion concentration is 2 times 10 to the negative 6 molarity. The first thing that we're going to do is write the equilibrium constant expression for water. Then I'm going to rearrange it to solve for hydroxide ion concentration. Next, I'm going to plug in my values, and then I'm going to complete the calculation. When I divide these two values, my final answer is 5 times 10 to the negative 9. And that gives me my hydroxide ion concentration. Let's do one more example. In this situation, my hydronium ion concentration is 6.5 times 10 to the negative 3 molarity. The first thing I'm going to do is write out my Kw expression. I'm going to rearrange my formula to solve for hydroxide ion concentration. I'm going to plug in my values, and then I'm going to complete the calculation. My answer is 1.5 times 10 to the negative 12. Let's do examples of calculating pH given a hydronium ion concentration. So the first thing that we're going to do is write our equation to solve for pH, which is given to you on your AP Chemistry reference tables. So pH is equal to the negative log of the hydronium ion concentration. Then we're going to substitute in 4 times 10 to the negative 8 molarity into the equation. In your calculator, you're going to put in the negative log of 4.0 times 10 to the negative 8. This will result in a calculated pH of 7.4. Let's do another example. So again, the first thing that we're going to do is write out our pH equation. We're going to substitute 3.2 times 10 to the negative 5 molarity in for the hydronium ion, and then we're going to complete the calculation. So the pH here is 4.5. Let's move on to calculating pOH. Basic solutions can be expressed in pOH rather than pH. The equation is similar to the equation to calculate pH. pOH is equal to the negative log of the hydroxide ion concentration. Calculate the pOH if the hydroxide ion concentration of a substance is 2 times 10 to the negative 10. So the first thing that we're going to do is write our formula. Then we're going to plug in our values for the hydroxide ion. Then we're going to solve for pOH. So the pOH is calculated here to be 9.7. Let's do another example. Calculate the pOH of a 0.02 molar solution of NaOH. So in this particular situation, we have to remind ourselves that a 0.028 molar solution of NaOH will dissociate into 0.028 molar sodium ions and 0.028 molar hydroxide ions in a 1-to-1 ratio. So that means when we calculate pOH, we're going to be using this molarity right here, as the sodium ion concentration is negligible because the sodium ion is just a spectator ion. pOH is equal to the negative log of 0.028 molar. And when we do this calculation, our pOH is equal to 1.6 molarity. Let's do another example. This one is a little bit different when we calculate the pOH because we have a 0.0011 molarity of calcium hydroxide. In this situation, the ratio of calcium ions to hydroxide ions is 1 to 2, and we need to take that into account before we can calculate pOH. So a 0.0011 molarity CaOH2 solution will dissociate into 0.0011 calcium ions plus 0.0022 molarity hydroxide ions. And again, this is because the ratio of calcium to hydroxide is in a 1 to 2 ratio. So the molarity that we're going to plug in to our pOH formula is going to be 0.0022 molarity. So you can't just assume that the concentration in front of a compound like CaOH2 is going to be exactly the same. You need to look at the mole ratio. So we're going to write our pOH formula, then we're going to plug in our values, and then we're going to solve for pH. So our pH here is calculated to be 2.7. If we wanted to take this a step farther and find pH, we can use the formula pH plus pOH is equal to 14. We can then rearrange this formula to solve for pH. substitute in our pOH value, and then solve for pH. So with a pH value of 11.3, this would be considered a basic solution. Converting pH into hydronium ion concentration. Let's look at an example. A solution formed by dissolving an antacid tablet has a pH of 9.18. Calculate the hydrogen ion concentration. The first thing that we're going to do is begin with the equation pH is equal to the negative log of the hydronium ion concentration. Then we're going to divide both sides by the negative. And then finally, we're going to take the anti-log of the pH, which is negative 9.18. So by taking the log of both sides, we have 10 to the negative 9.18. And if we take the anti-log of that value, the hydronium ion concentration is 6.61 times 10 to the negative 10 molarity. Let's do some examples. Converting pH into hydrogen ion concentration, then hydroxide ion concentration. So I'm going to show a couple different ways to approach this type of problem. So we're being asked to calculate the concentration of hydroxide ions in a KOH solution at a pH of 11.89. So for this first example, I'm going to start out by writing my pH formula. So pH is equal to the negative log of the hydrogen ion concentration. So the pH that's given to me is 11.89. I'm going to take the negative of both sides, which will give me negative 11.89 is equal to the log of the hydrogen ion concentration. I'm then going to take the log of both sides. This will result in 10 to the negative 11.89, which will equal my hydrogen ion concentration. So I will take the anti-log of the negative 11.89, which will result in a hydrogen ion concentration of 1.3 times 10 to the negative 12. The next thing I need to do, because right now I only have the hydrogen ion concentration, is to find the hydroxide ion concentration. To do this, I'm going to start out with my Kw formula. I'm going to rearrange my formula to solve for hydroxide ion concentration. Then I'm going to plug in my values. Completing this calculation, I find my hydroxide ion concentration to be 0.0077 molarity. Let's do another example. Calculate the concentration of hydroxide ions in CaOH2 at a pH of 11.68. This one I'm going to do a little bit differently to find out the hydroxide ion concentration. I'm going to start out with the formula pH plus pOH is equal to 14. I'm going to rearrange my formula to solve for pOH. I'm going to substitute in my values. I substituted in my value for pH. And now I'm going to solve for pOH. My final value for pOH is 2.32. Now that I have this pOH value, I can solve for hydroxide ion concentration. So I'm going to use the formula. pOH is equal to the negative log of the hydroxide ion concentration. So in a similar process to here, we know that ultimately we're going to arrive at the formula 10 to the negative 2.32 will equal the hydroxide ion concentration. So if I take the anti-log of negative 2.32, my hydroxide ion concentration will be 0.0048 molar. The relationship between pH and pOH. In pure water, a neutral solution occurs when pH is equal to pOH. So pKw is equal to pH plus pOH, which equals 14 at 25 degrees Celsius. Since pKw is equal to 14 at 25 degrees Celsius, pH is equal to pOH at 7. Worked example using density. A solution is 0.655% nitric acid by mass. Assume a density of 1.01 grams per milliliter for the solution. Calculate the pH. Nitric acid, HNO3, is a strong acid and will fully ionize in water to form hydrogen ions and nitrate ions. In this situation, we're going to assume a 100-gram sample of solution. In this 100-gram sample of a 0.655% nitric acid aqueous solution, there is 0.655 grams of nitric acid. So what we need to do here is take this 0.655 grams of nitric acid and find the molarity of the hydrogen ion but also taking into account that the density is 1.01 grams per milliliter of solution. So we're going to start this problem by writing out our mass of nitric acid over the total mass of solution. Then we're going to follow the AP chemistry mantra and convert this mass of HNO3 into moles of HNO3 because we need molarity. So 1 mole of HNO3 has a gram formula mass of 63 grams. Now that I'm in moles of HNO3 and I know this is going to fully ionize, my next step is to find moles of hydrogen ions. So for every 1 mole of HNO3, because this is a strong acid and it's going to fully ionize, I'm going to have 1 mole of hydrogen ions. So I have the top part of my molarity formula because molarity is equal to moles over liters. This is where the 100 grams of solution comes in and our density of solution. So then my next step is to turn this mass of solution into milliliters of solution. So because we have 100 grams of solution in the denominator, I need my 1.01 grams based on what was given to me in the numerator divided by 1 milliliter. This will cancel out grams of solution, and convert me over into milliliters. My last step is to take this milliliters and convert it into liters. 1 milliliter cancels milliliters in the numerator. I know that there is 1,000 milliliters in 1 liter, and I am left with liters in the bottom, which I want. I'm going to go back and check that all of my units cancel to get me into moles of hydrogen ions. So grams cancel grams, moles of HNO3 cancels moles of HNO3, and I'm left with moles of hydrogen ions. Now I'm going to do my calculation and figure out my molarity of hydrogen ions in this solution. So this will equal 0.105 molar H+1. Now that I have this concentration of hydrogen ions, I can calculate my pH. So I'm going to write my pH formula. I'm going to substitute in my values. I substituted in my value for my hydrogen ion concentration, and now I'm going to calculate the pH. So my calculated pH is 0.97, which I'm rounding up to 1, which means that this is a very acidic solution. Note that a change in the hydronium ion concentration by a factor of 10 causes the pH to change by 1 unit. To summarize, as pH decreases, the concentration of the hydronium ion, which is a measure of the acidity of the solution, will increase. As pH increases, the concentration of the hydronium ion, which is a measure of the acidity of the solution, will decrease, as we can see in this pH scale below. So what did you learn? We talked about the autoionization of water, the ion product of water, the pH scale and calculating pH, calculating hydronium and hydroxide ion concentrations, calculating pOH, and the relationship between pH and pOH. Need more help? Feel free to contact me. Have a great day.